Hello, everyone. Thanks for coming. Our next talk is by Amanda Sopkin. It's titled Randomness in Python, Controlled Chaos in an Ordered Machine.
Okay. All right. Hi, everybody. So today we're going to be exploring the concept of computational randomness, and we're going to frame our discussion in terms of Python. So we're going to start out by talking about why randomness is an interesting topic, why it's worthy of our discussion. And then we'll go through some examples of randomness gone wrong, of some weak random number generators that were leveraged for nefarious purposes. And then we'll talk about some of the early methods of simulating randomness and look at how they evolved to get us to the methods that we know and love today. Cool. So I want to open with this strip from Dilbert. Dilbert is being given a tour of accounting by a little monster, and the monster says, "Over here we have our random number generator," and he gestures to a little monster that is saying 999999, and Dilbert asks, "Are you sure that's random?" And the tour monster responds, "That's the problem with randomness. You can never be sure." So I wanted to open with this because it introduces a key theme of our discussion, which is the difference between true randomness in a mathematical sense and most of what we're actually using, which is generally pseudo-random. Cool, so randomness is an interesting topic for us because it makes processes secure, a lot of the important things that we're doing online. It's interesting on a mathematical computational level if you're thinking about the idea of writing an algorithm that will produce a random output. Also on a natural level in terms of the randomness of certain natural processes, and on a philosophical level as well. And as we'll see today, it is difficult to actually achieve in a pure sense. Cool, so why do we need randomness? So as I said before, randomness is a backbone for a lot of the secure processes that we engage in every single day. So if you're like me, you probably connect to Wi-Fi every single day. So when your computer connects to Wi-Fi, it sends a random nonce to the Wi-Fi access point, and the little number I have up there isn't representative of what it would actually look like. It's just an example. And then the access point sends back another random nonce, and then the computer and the access point continue their connection by sending these things back and forth. And randomness is a key part of this process because if you think about what it would look like if it weren't random, like every single time if my computer was connecting to a Wi-Fi access point, if it sent like 1, 2, 3, 4, and if the access point responded every single time 5, 6, 7, 8, obviously that's very predictable, and that would make that operation susceptible to attack. So the randomness in that operation gives us this level of security that we wouldn't have otherwise. And it's a similar kind of idea if you're thinking about like a computer connecting to a server. So some of the other operations that rely heavily upon secure randomness are if you're logging into Facebook, if you're video chatting, if you're sending encrypted email, if you're shopping online. All of those things rely very heavily upon having a cryptographically secure random number generator behind them. Great, so now that we understand why this is worth talking about, I'm going to introduce some terminology. So when we're talking about problems with a random number generator, it's going to be either with the starting point or the seed or the algorithm. So basically, if you look at a typical way of generating randomness, we'll start with some number, which is the seed, and then we'll go through a series of steps, which is the algorithm, to produce some output. So for most of the things that we'll talk about today, if they're not random enough or if there's some problem, it's going to be either because of what we're putting in, which is the seed, or the algorithm that we're using. Great, so I want to start out by talking about an attack a couple of years ago on a website called Hacker News that leveraged a weakness with their random number generator. So you may be familiar with Hacker News. It's like a Reddit similar forum where people can post news about the technology industry. And a couple of years ago, someone figured out that there was a problem with the random number generator they were using to generate user IDs. So I'm going to talk through loosely how the attack was executed. So first of all, the person figured out that user IDs were seeded with the restart time of the website. That's a decently common way to do it. And then with that information, they crashed the website. They predicted the restart time to within 60 seconds. So that gave them 60,000 possible seeds looking at all the milliseconds. They iterated over all of those possibilities to find the seed that was used. And then they used that to predict the assigned user IDs as people logged in. And then with access to those user tokens, they were able to impersonate people who are registered on the site. So this attack was partly possible because the person who executed it contacted the website and asked for permission. So they said, hey, I see this weakness. I think this is possible. Would you let me do it as sort of an experiment? And Hacker News agreed, and they provided them with the restart time of the site. But you can see how a similar kind of attack could occur without permission, like in the wild. And that is a popular way to execute a lot of attacks, is by leveraging a weakness in a random number generator. So next I want to talk about a historically controversial example of randomness gone wrong. So in 2004, the National Institute of Standards and Technology introduced this algorithm called the dual EC DRBG, or it's also called the dual EC PRNG, which is pseudo-random number generator. And we're not going to go into the specific details of how it works because it's very complicated. There are papers written about it, but it relies upon elliptic geometry. And it was known for a couple years, or at least speculated, that it had some weaknesses. But then in August of 2007, two Microsoft engineers, Daniel Chameau and Niels Ferguson, presented this paper at a cryptography conference entitled On the Possibility of a Backdoor in the NIST SP890 Dual ECPRNG. And try saying that 10 times fast if you want a little fun challenge. And basically, they demonstrated how using this weakness, they could predict the output of the algorithm almost every single time, which is a huge problem for a random number generator. So that kind of made some waves in cryptography circles, but it didn't get really big until fast forward 3 months later. In November of 2007, Bruce Schneier put an article into Wired magazine that was based upon the findings at that conference. And his article was titled, "Did the NSA Put a Secret Backdoor in New Encryption Standard?" So you can kind of see how the plot is starting to thicken here. It goes from being potentially just like a mathematical weakness that was missed to being speculated that it was put there deliberately by the NSA so that they could figure out the output of this random number generator. And to give you an idea of how serious that is, that would allow the NSA to determine the state of the random number generator and thereby eventually be able to read all data sent over the SSL connection. So if you're in the NIST and you are standardizing algorithms that are used for incredibly important processes like SSL, it is very important that no one should be able to predict the output of those algorithms. So that's why this is such a big deal. So fast forward a few years, in 2013, Edward Snowden leaked a series of classified papers, and one of those papers contained reference to a program called Bull Run, which is mentioned in this New York Times article, NSA able to foil basic safeguards of privacy on the web. And it said, one of the purposes of Bull Run is described as being to covertly introduce weaknesses into the encryption standards followed by hardware and software developers around the world. So you see, now we've gone from just a mathematical weakness, like maybe it was missed, to people speculating that it was put there deliberately by the NSA, to connecting the dots to this program that was designed to introduce these weaknesses to encryption standards that are being followed around the world so that the NSA could predict their output. So just to review the timeline here, in the next year, the NIST recommended removal of the algorithm as a standard. And to go over how long that took, in 2004, the algorithm was introduced. In August of 2007, Daniel Chameau and Niels Ferguson presented their paper on its key flaw. A few months later, Bruce Schneier put that into an article in Wired magazine. In September of 2013, the Snowden papers were released, and they contained reference to the Bull Run program. And then a few months later, in December of 2013, a presidential advisory committee was assigned to examine encryption standards. And the next year, the standard was finally removed. So between when it was created and when it was finally removed by the NIST, 10 years passed, so a decade of time. And during that time, it's not like this was the go-to algorithm by everyone. It was actually considered too slow for some purposes, but it was still standardized by the NIST, which is a big deal. So it managed to leak its way into a lot of important pieces of technology. So to give you an idea of the scope of that, there's this list of all the pieces of technology that were declared secure because they relied upon this algorithm and are now considered compromised once the weakness was revealed. So you can see that you can just like scroll through this forever and ever. Tons and tons of companies were affected. And it would be probably more difficult for me to name one that definitely wasn't impacted, but the list includes Microsoft, Google, Apple, McAfee, Docker, IBM, goes on and on. It also included the RSA B-Safe libraries for Java and C++. So this gives you an idea of the scope of the impact it can have if an algorithm that was standardized by the NIST turns out to have such a serious weakness. So now that you understand the stakes when randomness is done incorrectly, we're going to talk about how to do it the right way. So you want to talk about creating randomness. And most of what we'll talk about is more like simulating randomness. So I want to go over 5 qualities that an ideal pseudo-random number generator should follow. The first one is that it should pass certain statistical tests of randomness. So I just took a sample of 4 here. There is a suite of tests called the die-hard suite, and it's commonly thought that if a number generator passes all of those tests, it's considered sufficient for most purposes. So one of the more popular tests is known as the monobit test, and basically the output of the algorithm is mapped to either heads or tails, and then it's run a bunch of times, and we make sure that the output follows 50% heads, 50% tails, like we would expect. Some of them rely upon the concept of distance, like on a map. So the output of the algorithm is translated into locations on a map, and then we look at those locations and make sure there's no like weird clustering and that they generally follow an expected distribution. Another form of test relies on card games like poker or craps. So again, we translate the output of our random number generator into hands that could be played, and then we look at those hands and the outputs of a bunch of different games, and we make sure that they follow an expected distribution. And then the last one I'm going to mention is the birthday test, which relies upon the statistical concept of the birthday paradox. And basically, we map the output to a bunch of points on intervals, and then we look at all of the intervals between those points and make sure that they are exponentially distributed. So that's just kind of an overview of the kinds of tests that we might use to figure out that a pseudo-random number generator is good. Another big quality that is important is we want our pseudo-random number generator to take a long time before repeating. So that might surprise you that we want it to repeat, but we do. And we want it, obviously, to take a long time before it does so. And in mathematical terms, that is known as having a long period. Third of all, we want our algorithm to execute efficiently, meaning that we want it to be fast and take up relatively low storage. Fourth, like I hinted at before, we want it to be repeatable. And then fifth, we want it to be portable, meaning that we should be able to run the same system on any machine and we wouldn't have any problems, so it shouldn't have to be run on a Mac, for example. Great, so now that we kind of have that framework in mind for evaluating our random number generators, we're going to talk about some of the early ways for simulating randomness, and I've put it in quotes now because what we're talking about next is not truly random. So one of the most popular things you might hear about mathematically is known as a linear congruential generator, which generally takes the form x sub k is equal to a times x sub k minus 1, which is the previous term, plus c, and then all of that modded by m. So a and c are just constants, and m is typically the largest representable integer that we can use, and it's also the period of the algorithm or the length of time it will take before it repeats itself. So I did a very basic one. I made a3, c9, and m16, which is clearly not the largest representable integer. And then the seed is just 4394. So I'm going to demo that here. Great. So looking at this, we can see that we start with 7 and we end with 7. So we repeated ourselves after just 9 steps. And that makes sense because it would take us up to 16 steps to repeat ourselves, and we did. And you could see that when I ran it as an example, I got the exact same output, which makes sense. So you can see why this isn't sufficient. Most linear congruential generators are better than this, because obviously the numbers I chose were pretty small, but they are still not sufficient, so we're going to talk about some better methods of pseudo-randomly generating numbers. All right, so this is von Neumann. He's a very famous mathematician, and you may be familiar with him for designing a lot of how modern computers are architected. But it turns out that he also dabbled in randomness, and he created a method that was very popular for a couple of decades called the middle square method. And when von Neumann created the method, he said about it, anyone who considers arithmetical methods of producing random digits is, of course, in a state of sin. So basically, what von Neumann is saying is, if you're thinking about the idea of writing out like a list of steps that you're going to follow, and you expect the output to be random, on a practical level or a logical level, that doesn't make sense. So what we're doing is putting ourselves into a state of sin. So this is a general description of the middle square method. We start with a 4-digit seed, or it can be more if we like. We square the value. If the result that we get has fewer than 8 digits, or however many we're looking to double, then we add leading zeros, we take the middle 4 digits of the result, and then we repeat the process. So I'm going to walk through an example of what that looks like. So we start with the number 9834. We square it to get 96707556. There's no need to add leading zeros, so we skip that step. We take the middle 4 digits again to get 7075, and then we repeat the process. By squaring 7075 to get 500,55625. So that gives you an idea of how it works. And I wrote some code to show what that will look like. So we're going to run that here. And I'm going to enter the number 5859. And that's just, I picked it randomly. It's probably not random because my mind isn't random, but pretend it is. So we began with the seed 5859. And we repeated ourselves after 62 steps with 0. And if you can look here at the end, the last 4 digits are 24, 5, 0, and 0. So you can see that it's starting to repeat itself and converge to 0, which is a key weakness of this algorithm. So the problem, so this is again what it looked like when I ran it as a backup, and I got the same result. It repeated itself after 62 steps. So the problems with the middle square method, it's pretty slow for most purposes. It is statistically unsatisfactory, meaning it doesn't pass as many of those tests that we talked about as we would like it to. And the sample of random numbers that it produces might be too short for some purposes. So I wanted to graph it. On the left there, you can see an advanced linear congruential generator. And by looking at the output, you can see that it generally appears random to the human eye. And if you look at the one on the right, which is the middle square method, it certainly does not look random. It's clearly repeating itself. So this test doesn't always work, but it is an interesting way to visualize the problems with certain algorithms, and it does work in this case. Okay, cool. So now we're going to transition into talking about cryptographically secure pseudo-random number generators, which are generally referred to as CPRNGs or CSPRNGs. And we're going to start out by talking about one that is not cryptographically secure, which is the Mersenne Twister. The Mersenne Twister algorithm is the basis it's the most used pseudo-random number generator currently. And it's also the basis for the random module in Python, which is why it's interesting to us. It has a very long period. Its period is a Mersenne prime, which explains its name, which is 2 to the 19937, all of that minus 1. So very long time before it repeats itself. But it is not cryptographically safe, and we'll see why. All right, so I'm going to show you what it looks like when I graph the random module, which is based on the Mersenne Twister. Cool. So this is the first one that we showed before. It's the advanced linear congruential generator. It does appear random. And here's the random module, and it also appears random to the human eye. So in this case, this doesn't work, and we have to dig a little bit deeper to see exactly what is wrong with the random module. So that's another graph, what I just showed you. So what's wrong with the random module? So I want to preface this by saying that the people who designed the random module knew that it was not cryptographically secure. And if you go and look at the documentation, they're very explicit about that. They say that it should not be used for things like password creation, and they recommend that if you're doing that, you should look for something better. But the problem is no one reads the manual, and people continued using the random module for things that they shouldn't be for years. So I'm going to explain the depth of that problem. This is a bug that was submitted to Zope in 2012 by David Glick. Zope is a suite of web applications that's built primarily in Python. And he says, Plone, Zope, Paste, and possible other third-party components are using the random module where a cryptographically secure pseudo-random number generator is required. I suggest that you modify your code and replace the random module with either an instance of random.systemRandom or os.urandom. Improper uses for the random module are, for example, and then he goes on to list some like password creation, the generation of section keys, or the production of non-deterministic IDs like user IDs. So he's saying, I know that this isn't what we designed it for, but people are definitely using it to do this, so we need something better. This is a question that was submitted to Stack Overflow in 2010, and basically this person is just asking about creating a password in Python. And they mention using the random module, but they don't think it's the right way to go. And the first comment is, there's nothing really wrong with the second option, which is using the random module. Is it too slow? Do you need it to be faster? Are you running out of memory? So you can see that even though the creators of the random module explicitly told people not to do this, this person is doing it. And even when he asked, hey, I know I shouldn't do this, what's a better way? Someone said, no, that's fine. So later on down the line, I just think this is kind of funny. Someone else commented and said, just a quick FYI, the draft for the Python proposal, adding a secrets module to the standard library just came out, and it specifically links to this question and an answer. So when they created the secrets module, they specifically used the Stack Overflow question and answer as an example of why the random module is not sufficient. So that kind of tells us where we're going. So now we're going to talk about the secrets module, which finally is cryptographically secure. The secrets module, as I said, is cryptographically secure, and it includes a lot of sort of plug-and-play batteries that are made for people who don't want to build their own methods to do things like create a token or a password. And it uses 32 bytes of entropy by default. Cool, so a brief note about entropy. You're probably familiar with the concept as the measure of how disorganized the universe is. And when it comes to mathematical terms, when we're talking about randomness, it's less of a measure and more of an estimate of exactly how random something is. And it's difficult to explain / understand, but the way that I like to think about it is the likelihood that the output of a random number generator is just as likely as any other output. So I just think this is interesting, but there are naturally occurring sources of entropy that can be used to create random number generators, like, for example, atmospheric noise, lightning discharge, and thermal noise. And there are papers written about using those sources to create random number generators. But the problem is that they're potentially blocking. So if I used this in my software, and I didn't have enough entropy in my pool, then I might have to wait for more lightning to strike, and obviously that's not practical for most software purposes. But it is kind of a fun idea if you're interested in looking into it more. So this is a source code of the secrets module, and we don't have to go too in depth. I just want to point out a couple of things. First of all, it's importing system random, so you might remember that David Glick, who submitted the bug to Zope, mentioned using system random instead of the random module. The default entropy is set to 32 bytes, which is more than sufficient for most purposes. And you can see that it's, just by the length, not very mathematically complex. It's not like this huge, crazy algorithm. It's using existing means within Python to create randomness. And this matches what we talked about earlier. When the random module was designed, they said, don't just use this, look for other methods to make it better. And the problem is that people just weren't taking the trouble to do that because no one reads documentation. So they decided to standardize this and just make it really easy. So system random uses the OS as a source of randomness. It is not available or the same on all systems, so it's not perfectly portable in the sense that we talked about earlier. On Windows, it relies on something called cryptgen, and on Linux machines, it relies on dev random or dev urandom, which we'll talk about next. It doesn't rely on software states, and the sequences it produces are not repeatable. So now let's talk about dev random versus dev urandom. So dev random is purely random. It will block without sufficient entropy. So it relies on something called the kernel entropy pool, which basically pulls from a number of external sources. Like, for example, if I'm typing in keys, the speed that I'm doing that, or if I'm moving the mouse. But if it doesn't get enough entropy in its pool, it's going to block and wait until it has enough. So for that reason, it's slower than dev urandom. So dev urandom, which is what we generally actually use, will not block without sufficient entropy. It relies upon the same pool, but if it doesn't have enough, it'll use a cryptographically secure pseudo-random number generator to get there. So it's faster than dev random, but it is theoretically vulnerable to attack. And I put that in red because there's no documented example of this happening. And to give you an idea of why that would be really difficult, I would have to know like all of the entropy sources that are being used and how they're being translated through this algorithm that's permuting them. And it's not very likely, but if you're doing something like designing an algorithm that could be used for SSL, then you should use dev random because it is purely random, and dev urandom is not. Great. So I want to give you a couple of examples of the secrets module to show you how easy it is. So we're going to use it to generate some tokens. So it printed a 16-byte token and a 10-byte token, and you could see that the code that I used to do that is pretty basic looking. And then we're going to look at how it would work for password generation. So again, pretty simple to create an alphanumeric password. Great. So that's how a couple of those batteries that are present in the secrets module work. All right, so now is the point where I have to tell you that the secrets module is not the end-all be-all answer to this story. There's a kind of, I think, a moral to this story where even though the people who wrote the random module told people not to use it for cryptographic purposes, they continued to do so for like years and years. And eventually they said, okay, we're just going to make this super easy and create something that does it for them. But this isn't where we stop, and it's not the answer to all of your cryptographic needs. So this is a quote from the secrets module. It refers to something called the nuclear reactor of randomness in Python, which is cryptography.io. And it says, folks really are better off learning to use things like cryptography.io for security-sensitive software. So this change is just about harm mitigation, given that it's inevitable that a non-trivial proportion of the millions of current and future Python developers won't do that. So they're saying we've learned our lesson, and we're going to give you something that 95% of people can use for safe purposes. So basically you have your random module, which you could use like in an interview or if you're designing a game. You have your secrets module, which you can use for things like password creation or session keys. And then you have cryptography.io, which is for like that 5% or that 2% of cases that require something more secure. All right, so this is a screenshot of the docs of cryptography.io. It says, cryptography includes both high-level recipes and low-level interfaces to common cryptographic algorithms, such as symmetric ciphers, message digests, and key derivation functions. So we're not going to go into these things today. They're sort of outside the scope of this discussion. But if you are interested in looking into it, I encourage you to do so. It looks very usable. Great, so let's wrap up. What did we learn today? So randomness is very important for securing a lot of the things that we do on the internet, and we can thank it for that. It is difficult to truly achieve in like a purely philosophical or mathematical sense, but it can be simulated in a way that's going to work for pretty much everything we need using some of the methods that we talked about today. And I'm not going to do a formal Q&A, but if you have something to say, you can tweet me or find me at the conference. And with that, thank you everyone for coming, and have a good rest of your PyCon.